Hello and welcome to the first part of the directions video for the Pendulum Lab. Here I'm just going to show you an example of the equipment and how you would go about using it. And in the second part of this video, I'm going to talk about how to do the analysis in Excel, which is more involved than the actual procedure of measurements. All right, so here you see I have made a little pendulum bucket out of a cardboard core from a toilet paper roll, and I've attached it with twine to a light above. Okay, so I made a quite long pendulum. Yours does not have to be as long, but if you do have this vertical space, maybe outdoors, for example, then it can give you some extra flexibility for getting a range of significantly different lengths on your pendulum cord. This is the L that shows up in the description video, L being the length of the string or length of the cord. I'm not working outside today, by the way, because it's windy, so that's something that you do have to consider. If it is a still air day, then it works fine outside. If it's windy, it doesn't. Right now I have the pendulum cup empty. That isn't really recommended because if it's too light, things won't work that great. But I have 5 different weights that are just rocks. I would have weighed these ahead of time on a scale, and then I'm going to put them in one at a time because those are going to be my 5 different weights. All right, so for example, let's put in a couple of weights. Okay, so in this case, I have 4 rocks in there, and then I would just take the sum of those 4 rocks, okay? And again, you're gonna do 5 different weights, all right? And for 5 different weights, you'll do one particular release angle. So for example, I would do a release angle of whatever angle that is, 5 times with a different weight each time. Then I would choose some fixed weight, say with 4 of the 5 rocks inside, and then release the pendulum from 5 different angles. Okay? Then I would choose a fixed weight, say 4 rocks inside again, and a fixed angle, one of the 5 different angles that I experimented at, and then I would do 5 different lengths. Okay? So that's a total of 15 releases and 15 recorded swings that you're going to do. Right? So you're not doing every combination of weight, string length, and release angle. Instead, you're holding the other 2 variables fixed and only varying one at a time. Okay, I explained this in procedure, but I wanted to mention it again. Now, I want to talk a little bit about the idea of release angle. In order to do that, you need to measure a couple of things. All right, so here I have measuring tape. All right, I would have measured the length of the string. So that would just be the length from the center of my toilet paper cardboard core up to the fixed point on the ceiling above. Okay, that's my full length, that's my L. Then I would lift up the cardboard core to a certain height, and then I would measure the change in height of the center. Okay, so I would have a height that I measured relative to the floor, is probably a good way to do it. So I take my tape measure, I measure from the center to the floor below, make sure that it's vertical, okay, maybe by holding it against something that's straight. Then when I lift it up a certain amount, okay, then I would measure from the center to the floor a second time. Those 2 changes in height and the L, along with a little bit of geometry and trigonometry, will allow you to calculate your angle, okay? If you have questions about that, please ask me in office hours or during class meetings, and I'm happy to go over how to draw the picture and to actually calculate the angles based on those lengths. All right, it's all about making triangles out of those lengths. All right, now the last thing I'm going to show you in this part of the video is just releasing it. So let's say that I made those measurements already. I release it to a certain height. I made sure that that angle is less than 15 degrees. So maybe something like that. All right, that's probably less than 15 degrees because that's your small angle approximation. In part 2 of the lab, you're going to want to make sure your angles are really big. So something like this, right, where you're releasing it very far. But then when you release it from a small angle or very far, what you want to do is let it go and then let it do 10 complete swings. The reason you're doing 10 complete swings is because otherwise there's going to be a lot of error in stopping and starting your stopwatch for just one swing. You minimize that error by having 10 complete swings and then just dividing by 10 to get the time of a single swing. Okay? So what you would do is you'd have, okay, so a complete swing is this. To the side and back. Okay, that's a complete swing. That is one The time for that to happen is called 1 period of the pendulum. So again, complete swing. Okay, when it gets to the far side, that's just half a swing, half, full swing, all right? So 10 complete swings would be 1, 2, 3, 4, and you get it, right? And you just count the 10, measure the total time it takes to do 10, and divide by 10. All right, so stay tuned for how to do the analysis in Excel. All right, so continuing on with the second part of the lab, I want to talk about how to create the predictive data in Excel. Now, this is a different way of using Excel than we have before, where we enter data into Excel that we collected and then analyze it in some way by creating a graph. Instead, we're actually going to use Excel to create an approximation of real data and then see how that compares to a measurement of period. And you'll be measuring period the same way that I mentioned in the first half of this video, having 10 swings and dividing by 10. Okay, so let's go ahead and create this graph here, the graph that I explained at the beginning of Procedure 2. And this whole idea of using Excel only applies to Procedure 2. In Procedure 1, you're just going to be taking measurements of period with your actual physical pendulum, and as I mentioned, varying the mass, the length, and the initial angle of release of the pendulum. Okay, so let's create our 3 columns here. So we're going to have time, all right, measured in seconds. All right, and then we're going to have the angle measured in radians, okay? Now the reason we're using radians and thus having to convert back to degrees, because I assume that we're going to be using and thinking of degrees for everything else, is because Excel uses radians. It's just the native angle measurement of Excel. All right, and then here we're going to have pendulum mass velocity, okay? And the mass just refers to the thing at the end, okay? All right, and that's just in meters per second. All right, the little bucket, the toilet paper holder, that's the mass. Okay. All right. So the first thing we want to do is actually create the time. And the way we're going to use this is we're going to use Excel's kind of pattern recognition. So the first time is going to be time 0. And then you're going to create the second time is 0.005. Because you're going to be measuring in segments of 5,000ths of a second. Okay. And then we'll go ahead and create the third one, which would be 0, 1, 0. Okay. And then I'm going to select all 3. And then when I drag this corner, look what happens. Excel automatically figures out that I'm going in steps of 0.005 and then it starts advancing in that step. And I'm just going to continue on until I get to 2.5. Okay. So I went a little too far. Okay. So here we are, 2.5. So you see it takes 502 rows to get to 2.5 in steps of 5,000ths. Okay? All right, so a lot of rows, right? But Excel's going to do all the work. It's not, we're not going to be filling anything by hand. Now the angle. So we fill in the initial angle of 0. So what does that mean to have an angle of 0? That means the pendulum is completely vertical, right? The string is totally vertical. It's in the same direction as gravity. Well, in order for the pendulum and the mass with the rocks at the end to be completely vertical and lined up with a vertical string, then the pendulum has to be in motion. Because think about that, because you released it, you lifted the pendulum to a certain angle, and then you let it go. So as it passes through that lowest point, at which point the string is vertical, it's in motion. In fact, it's moving as fast as it's ever going to move. But that's where we choose to start our measurement. And that's actually a different starting point than we start with when we measure the period with the stopwatch and just observing the swings. There we start the period at maximum release, where the velocity is 0 and the angle is maximum. But it doesn't matter. It doesn't matter where your starting point and ending point is, as long as you get back to where you started. Okay? And you'll see that shows up in the graph. You can still clearly identify what is the full period. Okay? But the reason we're starting here is it's mathematically easier for Excel to start at the bottom of the swing. It corresponds to a 0 degree tilt angle relative to the vertical and maximum velocity. But that means I need to find my maximum velocity. How do I find the maximum velocity? Well, I'm going to use conservation of energy in a really similar way to our conservation of energy lab. As it turns out that a swinging pendulum exchanges gravitational potential energy for kinetic energy in the exact same way that a falling ball does. The path of the swing doesn't matter. And that's because it turns out that gravity is a path-independent force. All right? So here's the calculation. What we do is we would use 1/2 mv squared equals mgh. Okay? That's the calculation we're going to use for energy conservation. Okay? So for example, and notice in this equation that m would cancel. right? So the m is going to cancel on both sides. And so then what I'm going to be doing, and here, let me do one thing so maybe we can see this. So I guess you can see it okay. Okay. So that would just become 1/2 v squared equals gh. So then I want to solve for v. So then v is then going to equal the square root of 2gh. Okay, and all I've done there is just do some algebra to isolate v. All right, SQRT is just using the notation of Excel. All right, so the way I have it written isn't going to give me a number, but check it out. If I ask Excel to give me a number, and I could do this in my calculator, but I could just do it here in Excel, and then could put in that same notation, square root, and notice now that Excel is recognizing that that is a function. It actually wants to do the math. The reason is because I have that equal sign in the front, right? So then I'm just going to put in 2, and then times 9.8 because that's gravitational acceleration, and then times the height. So the height is just what I mentioned in terms of measuring the height, or the distance or the height from the floor to the center of the toilet paper core when it's vertical, and then measuring again when you lift it up to a certain angle. Well, that's that difference between those two measurements from the floor would be your height, because it's the height relative to its low point. So let's say in this case it's 20 centimeters. Okay. All right. There we go. Good. All right. And then one thing that I also want to make sure is that I consider the length of the pendulum in this case. So up here I'm just making a note of that. So I'm going to put that the length of the pendulum. Well, if I have a 20 centimeter lift, if I want that to correspond to a large angle, something bigger than 15 degrees, I want to make sure that my pendulum string isn't too long. So let's be safe and just make the pendulum string twice as long. Let's make it 40 centimeters long. So 0.4 meters. Okay. And so there I just have kind of a quick note here, and let's put some units on that. Okay. And then over here, this would be this would have units in meters per second, but I can't add the units because it's a calculation. Okay. Over here I can though, just to make note. This is meters per second. Okay. All right. So again, it was important in my kind of hypothetical case of imagining the data that this would correspond to, because ultimately you're going to want to make sure that whatever length you propose here that you have Excel predict, you want to make sure that length matches up with the real length that you're using. And as I make the suggestion in the lab handout, it should be a shorter length for these large amplitude releases so that the height doesn't have to be incredibly high, because you want the angle to be pretty big. You want to have like a 50-degree release angle or something on your biggest end. Okay. So there we go, and again, this is going to be in meters per second, 1.9798 yada yada. Okay, that's how fast it's going when it passes to the bottom of the swing, which is the fastest it will be moving, because the pendulum, it starts from rest, speeds up as it gets down to the bottom, and it's fastest as it goes to the bottom. So I'm going to go ahead and copy this number. Now, one thing I got to be careful if I just copy over this number into this place, because that's the maximum velocity. It's gonna try to copy over the formula. So what I'm going to do is I'm going to click on this and do Control-C to copy it. But then when I click on the cell where I want to put that number back in, I'm going to do Control-Command-V and just enter the values. Okay? You can also right-click and choose Paste Special. That's the menu. And that way Excel won't get confused and is just pasting the number. Okay, now I'm ready to actually start doing my recursive calculation. And I'll remind you what recursive means in just a moment. Okay, so let's go ahead and fill in the cell. So it says here, referring back to the lab handout, that in this next cell, so the cell in row 3 essentially, or the second row of actual numbers, because the first row is just titles, it says calculated with the specific formula below. Okay, well, which one is that? Well, it says here, second, calculate subsequent pendulum velocities using the following formula. Okay, so the first thing it actually wants me to fill in is this cell here, if you're actually reading through the body of the handout. Okay, the reason I put that in there is because that's kind of it just kind of intuitively for me is the kind of the first thing I would fill in. So essentially you're going to fill in this cell that the cursor is over, and then this cell. So let's indeed start with this one right here. So that would be C3. All right. So what am I going to enter in C3? I'm going to enter this formula. So a quick note about this formula. Let's zoom in on it a bit. As we look at it, so it's V of t plus delta t. What the heck does that mean? Well, that means that you're actually just in that is t plus delta t is actually referencing the current row, all right? Because t is the previous row. So t plus delta t would be row 2, all right? Well, again, row 3, right? But row 2 of numbers. I'll just refer to it as row 3, all right? So t plus delta t is row 3. Meanwhile, t, it'd be row 2. So let's see how that works then, okay? So I'm going to go ahead and start with an equal sign. So I'm telling Excel I'm going to do a calculation. So then the first thing I want to do is enter v of t. And remember, then v of t must be a velocity, so it must be in the same column, the C column, but it must be the row above because it doesn't have the delta t. Get that? So it ends up being C2. Okay? So again, if v of t plus delta t is C3, then v of t must be C2. Okay? Because it's the row above in that same column. Then subtraction. Okay, so notice I put the subtraction sign in there. Then minus delta t. Well, what is my delta t? Well, it's 5,000ths of a second because every single row advances one segment of time, one delta t, which is 0.005 seconds. So 0.005. Okay? All right, then multiplication on the multiply by g, so 9.8. Okay? And then times, now it wants sine of theta t. Okay, so the theta column is the B column. And since it's theta t as opposed to theta t plus delta t, then it must be the row above. So that means that this must be sine of B2. So first of all, I put the sine function, okay, most recently used. So I want Excel to realize that this is actually a function. Again, Excel's going to be looking for radians. So that's what we're using. And then I'm going to click on B2. Okay, close parentheses, done. All right. So here, notice that it didn't actually have any change in velocity yet, okay? And that's, but it will once we start putting in more calculations, all right? Let's go ahead and do the same thing for column B using the description here that starts with the word third, okay? So third, calculate angles of the pendulum beyond the initial value of 0 radians using the formula, all right? So again, here, theta of t plus delta t refers to the current row in the theta column, so that would be B3, which I already have highlighted. All right, so let's start a formula here by putting the equal sign. And the first thing is going to be theta of t. So that's going to be the same column but the row above, so B2. All right, and then plus delta t, 0.005. All right, and then multiply by Vt. Okay, so then that means that would be the velocity column, but the row above, so that would be C2. Okay, and then divided by L. Well, I decided to do a L of 0.4 so that my height of 0.2 is indeed a large angle. So be consistent with my length, 0.4. Okay, there we go. Now we're ready to start filling these in. Because all I need to do now is just click on that calculation and just pull it down, and then it will refer to all the cells that are in the same orientation. So let me just pull this down a few. And I'll pull this one down a few as well. Right now, look, it seems like it's not working, right? It's just repeating itself. That's because I need to pull down both of them in order for it to work. Okay, now it's working, right? Now the numbers are changing in both columns. And let's just show you what I mean by that the Excel figures out the pattern. So look here, when I click here, the formula that I entered here referred to the column above, or excuse me, the row above, and referred to both columns for calculating the velocity, the instantaneous velocity. Likewise, for the instantaneous angle, it referred to the row above and both columns. All right, and see, it's doing that. All right, and the numbers are changing accordingly. So the fact that the calculation refers to the value from before, that's actually the definition of a recursive formula or a recursive method approximation. That's what this is. We're making an approximation by doing a recursive formula where we do a repeated calculation, constantly referring to the number that we just calculated before. It seems kind of circular reasoning or cheating or something, but the reason it works is because we're doing really small time steps, and the physical assumption that we're putting in the time steps, which by the way is constant acceleration, is pretty good, because it turns out if the segment of time that's passed is really small, then the acceleration hasn't changed much. So then we are actually making a good approximation and thus modeling something that has no formula. There is no known formula to physics that would actually summarize this data. It can only be done numerically like this. Okay? All right, so let's just continue it. We're going to continue all the way down to the 300 rows. So I'm just going to click on the corner, right, and just keep dragging it down. Right? It doesn't take long at all. Right? 502 rows. Do the same thing for instantaneous velocity. There we go. Not bad, right? Okay, so then what we want to do is that we want to calculate just time versus angle. You could do time versus velocity, it doesn't matter. So actually you could graph
these two against each other, and I just held Command in order to select two rows that are not next to each other, or I could just just mouse over these two rows like this and just select them. By clicking on the letter at the top, that tells Excel I want to select the entire column. Excuse me, I keep calling it row. But by clicking on the letter on the top, that means I want to select the entire column, see? Otherwise, if I click on, say, the title, it just selects that single cell. If I click on B, it selects the entire column. So anyway, I can graph these two against each other or these two. It doesn't matter because, I hit the wrong button. Because in either case, the whole purpose of the graph is just to find out how much time it takes for the obvious sinusoidal graph to repeat itself. Because that's the amazing thing, is this somewhat random looking formula that we entered is going to give us a sine curve, okay? So let's go ahead and just do A and B. All right, so I just select those two, and then I'm gonna go to Insert. I'm gonna insert a scatter plot right there. Look at that, it's a nice sine curve, right? How do we get a sine curve out of that? Because of math, that's how, okay? So let's look at this, all right? So I'm looking for a full period. A full period is just the time for the cycle to repeat itself, all right? So in that what looks like a swing when we're observing the actual pendulum motion is a sine curve in terms of like the actual data of angle or velocity. All those, the actual measurements you could make are going to be changing in a sinusoidal fashion. So that means if I look here, okay, so if I start at time 0, right, so if I go up and come back down, that's half a period, because then I have to go the other way. Because think of it, this would be like swinging and then coming to the midpoint and then swinging the other way and then coming back to where you started. So you have to get here until you've done a full period. And if you see, when I mouse over, it actually tells me that data point. And if I look right here at the first value of that coordinate, because you see in parentheses it says 1.365 comma negative 0.02, right? So that data point, as close to 0 as possible, which one's closer? I guess that one right there, 1.37. Okay, and I could even like scroll over the actual data and find the one that is closest to 0. But the graph gives you kind of an idea of where to look. So I know I should be looking somewhere around the 1.3 range. So let's go ahead and do that real fast. So let's go down to 1.3 seconds. All right, and I can just click away from this, and I'm going to look for the point where the angle becomes closest to 0. All right, because that's getting back to where I started. All right, so let's look here. Here the values are getting really small. Yep, it's this one right here. See, where it's 0.00, because just above that, so a moment before, 0.005 of a second earlier, the angle was slightly larger, and then 5 seconds later it's larger again. So this is where it gets closest to 0 at that particular point. So that corresponds to a time of 1.370 seconds. Important to include the 0 because we do have 3 significant digits after the decimal, right? So 1.370 is the period of this pendulum as predicted by this recursive method with an accuracy of 0.005 of a second. We could get probably a better approximation if we were doing steps of 1,000ths of a second and so on, right? But it doesn't matter because this accuracy is definitely as accurate as you're going to get it in terms of actually using the stopwatch. So now that you have this number, you're then going to go to your physical pendulum, raise a pendulum that is equivalent to this angle, release it, and in other words, get a pendulum that's 40 centimeters long, raise the mass at the end to a height of 20 centimeters above its low point, release it, measure its period, and see if the period is indeed 1.37 seconds long, right? And it should be close. But what's interesting is that it will be different than if you use the formula that said that the period is independent of the release angle. Because in procedure 1, we're all about saying that the period is independent of the release angle. And it should be. That's what your data should tell you. But when you do the large angles, it's no longer independent. Instead, it's dependent on this approximation. Or at least we'll see how good it is, right? Because it probably depends on how much air resistance there is for your particular setup. It depends on if you have extra vibrations, extra rotations, all these things that can go wrong, right? But that's all part of the puzzle, okay? So hopefully this makes sense in terms of how to set up the data and how to do the calculation, all right? Of course, I will be available throughout the week to answer any questions about this lab, and let me know. All right, thank you for watching this lab directional video.